said never start a presentation with an apology, so I'm going to start with two right away. One is that I took my jacket off because it was a little warm in here, and I couldn't bear to put it back on, but I promise you that's as far as I'm going to go. And the other is we might have some Mac PC font translation problems here, which are entirely my fault. So if it looks like some of my slides were done last night in the middle of the night after a couple of beers, you'll know why. But in any case, we're going to talk a little bit, or a lot. We're going to dissect a project that we're doing at CLEAR. One slide intro. Center for Land Use Education Research is about 10 years old, but it's built on a number of other programs that are much older than that. We are kind of a tripartite project between the Department of Extension, the Department of Natural Resources and the Environment, and the Connecticut College program, which is right down here at Avery Point, Groton. And what we try to do, our goal is always to have real integration between our research, which you're going to hear ad nauseum in a couple of minutes, our geospatial tools and training shop, and our outreach program. And because I'm not going to talk about those, I just wanted to mention that probably 80% of our effort is with our outreach programs, even though we're going to be talking about the research behind them right now today. So let's just skip that, because that tells really the whole story. Our target audience, for the most part, I mean, we have many target audiences, but the people that we think of when we do our research and our outreach are generally local land use decision makers. So those of you that aren't from Connecticut might not know, but those 169 towns, we have not had county government in Connecticut since the early 50s. And land use is decided on a town-by-town basis by local boards and commissions made up of volunteers. They may be elected, they may be appointed, but they're basically non-professional volunteers. And those decisions collectively dictate the landscape that we're talking about today and tomorrow in this conference. I'm basically going to pick apart our land cover research, take a little bit of time to go over the statewide results, and then look at the different components, major components of the land cover. And I'll explain to you what land cover is in just a second. There's lots more than this, not only on the projects I'm going to be talking about, but on all those other projects at our website at clear.uconn.edu. You've been looking at a lot of beautiful aerial photos. You won't be seeing as many here today. This will be the map portion of this afternoon's, and I apologize for it in some ways, but it's really nature of the beast in terms of talking about our research. So let's look at an overview. The project I'm going to talk about we call this CCL, Connecticut's Changing Landscape. It debuted in 2004. At that point we had 17 years of remote sensing data over 4 dates. Its whole purpose is to enable us to talk about land cover change by comparing apples to apples. So the remote sensing platforms change slightly. You may do something in 1997, and then your 2002 data set is almost the same, but not quite. And it's not really fair or appropriate to really judge, compare them directly. So we went back as far as the remote sensing platforms could allow us, which is 1985, the Landsat, which was then the new Landsat sensors, and went up into as far as we could into the future so that we could specifically chart change. We do hope to have a 2010 update later this year. So we have to have a couple of explanatory slides. What is land cover? You're looking at a remotely sensed image, a land cover image of the base of the Connecticut River, just west of here, Old Saybrook and Old Lyme. When we first started talking about this stuff a long time ago, nobody knew. I had to describe what a remotely sensed image was. Now it's part of everybody's lives, as is GPS and some other geospatial technology. But the point is that your eye can pick out a lot of information out of this image, but your eye cannot quantify what's going on there. So in order to quantify it and look at change and look at characterization of our landscapes, we have to turn it into a land cover map. Now, land cover is literally what's on the surface of the Earth. So the satellite sends out a signal, it bounces back, and the spectral qualities, the spectrum of the light that comes back to the sensor is what determines is it mostly green forest, is it mostly black pavement, etc. Obviously, most of the speakers in the next 2 days and a lot of the implications of what I'm going to tell you relate to land use, but that's what's planned, practiced, or permitted in a given area. So in our little example here, that forested area, all we know and all I'm going to be able to tell you about is that it's forest. I don't know if it's preserved open space or it's slated for a Walmart tomorrow and zoned commercially. And why do we look at land cover? Well, one is because the platforms allow us to do it at large scales over large periods of time. I think the Changing Landscape Project is nationally unique in terms of the length of time and then the detail of what we've done, but it's also being used nationally like this for large landscape analysis. And the other thing is because it is physically what's on the ground, it relates more directly to what we see in the health of our water resources, our forest resources, etc. And there's a growing and in some cases quite robust literature looking at the links between land cover and environmental health, particularly water, which I'm going to focus on a little more than some of the others. So lastly, what we do is we take that Landsat image, we turn it into a land cover map, and very important caveat, this is 30 by 30 meter pixels. That's another word I used to have to describe. It's short for picture elements. Maybe some of you didn't know that, but you probably did. And so it's 100 foot by 100 foot chunks. And so we're not looking at that high resolution image that we're all used to looking at. We're all spoiled about that. The computer and the analyst are taking that and chunking it up and saying most of that 100 by 100 foot piece is green, most of that 100 by 100 foot piece is paved over, etc. So it's very suitable for large scale and even pretty small, down to much smaller than a town level, but you're not going to be looking at the kind of subdivisions you were just looking at with our land cover data. It wouldn't be useful or appropriate. So let's look at where we are, and where we are, unfortunately, because this stuff takes time and effort, is 2006. So if I slip and say today, I'm talking about 4.5 years ago. There you see the typical land cover map. You're going to get sick of this particular map. About 59% in forest. The colors you're going to get used to, the red are developed land, 20%, and I'm going to say more about each one of these. So yellow turf and grass, so manicured turf and grass, which is very closely associated with development, and the brown being agricultural fields. And as you might expect, our websites, we try to provide this information in all sorts of formats: charts, maps, data, town-level maps, watershed maps. As we look at the towns, because we often do chunk up our data by towns, even if it's, perhaps scientifically more appropriate to look at it, for instance, in a watershed format. We also provide it in town format because that's the basic building block of land use decisions in Connecticut and really in most of the country. This is our range, so up in the northwest corner in Canaan, about 4.7 of that map is red or developed. And the other endpoint, Bridgeport, 82.5% is developed land. If we look at the overall trends, this isn't going to mean a lot to you, except for the green is slowly declining and the others are, most of them slowly rising. But why I left this one in is not for the magnitude of the data, but for the way it varies. So you can see that here in the land of steady habits, we haven't had any huge jumps, huge, phenomenal increases in the rate of development or in anything else. We have had a few, and this could be a little misleading, this chart, but basically it's been a slow and steady amount of change. And here's a bar chart that just summarizes that change. Now we're talking about 21 years of change between 1985 and 2006. So we're using big units. So the vertical axes are square miles. So we've gained about 150 square miles of what we call developed land. Again, I'm going to talk about that a little more. And about half again as much of this very closely associated turf and grass, which is the bright green manicured landscape. The other grass I'm going to talk about right now for a second and then pretty much ignore it. It is not, it's long, unkempt, unmanicured grass. We distinguish it from agricultural fields in various ways, and we distinguish it in grass because it's not bright green. It's not, however, mostly beautiful natural meadows with butterflies flitting around. It varies very closely with the developed classes, and so we think it's mostly the unkempt verges of highways, sides of airports, etc. And what makes us feel good as researchers is, might not make us feel good in terms of land use planners, is that if you take the big three winners, if you want to call them that, and you add up the change, over 21 years and over all these hundreds of square miles, they almost exactly, to, I don't remember, but 6 or 7 square miles or 5 square miles, balance the decreases we see in our other two classes, which are agricultural field and forest. This is just taking that same data, dividing by 21, and changing from square miles to acres, and it's just, I'm not sure how legible that is, but some people like numbers, so you could look at, we average around 5,600 acres of forest loss per year, gain 4,400 acres of developed land per year, that kind of thing. So what I'm going to do now is break down the 4 major categories and a little bit, one extra thing that we're going to talk about, riparian corridors, and break down the land cover and just say a little bit about it, and if there's significance in it to the issue of the day of smart growth and sprawl, and I think there is. I'll try to point it out to the extent that I can. Let's talk first about developed land. Here is a little explanation needed. Again, remember we're talking about land cover. So these areas are areas that are predominantly, well, they're dominated by rooftops, roads, concrete, and other what we call impervious surfaces, which is a term and a concept in the literature that's very strongly linked to the impact of development on water resources. Now, we are not showing developed parcels, so you can see this little map to the lower right. That's a subdivision. Pretend that subdivision is totally built out. There's a house on each one of those. That's 100% developed if you're a land use planner, and that's a totally valid way of looking at it. That's not what we're going to be showing, though. We're going to be showing the rooftops and roads as developed, the trees around that houses as green forest, etc. So, again, in some ways you can think of our developed figures as being an underestimate, for sure, of the amount of land that's influenced by development. Again, impervious cover, very important concept. I thought this was an appropriate slide. This is actually a sculpture, but any one of us could have taken this slide in the last 2 months. It was a very common phenomenon. I still see a car buried in the snow every once in a while along the road, but this is actually a sculpture somewhere in the Midwest. And what the literature tells us is impervious cover, as I said, is a very good indicator of the impact of development on waterways. And it mostly starts with this. We have a hydrograph, which is a fancy word for charting the flow in a water body over time. So we have flow rate on the vertical axis and time as a storm continues on. So we have our little storm here, and in a forested landscape, the hydrograph will proceed something like this. There won't be any rise in the stream for quite a long time because most of that water is going into the soil, being absorbed in the interstices between the soil particles, then a slow rise and a slow decline as the storm goes away. In a ultra-urban landscape, the hydrograph looks something like that. So what you have is more runoff, is represented by the difference in the difference in the area between the two curves, arriving quicker, which is represented there by the difference between the two peaks of those two curves. And what you end up is much flashier and more dramatic pulses of water into your water systems, which are not, Mother Nature did not design them to handle water in that manner. And of course that runoff has all sorts of associated pollutants with it as well. So again, the literature tells us that it's a good indicator. There are a number of caveats. I could give a whole talk with a number of experts here about impervious cover because new urbanists are interested in it, because sometimes if someone focuses too much on impervious cover, it might mean that they're not in favor of density. It's not been my case that that's what's going on, but the key points here are that we have a robust national research body of knowledge on this. There's been statewide recent Connecticut research that, again, supports this idea that impervious cover is a great indicator of the role of impact on water. I think it's going to be the new trend in Clean Water Act regulations, which we don't have time to talk about, but many municipalities and other regulated entities are going to be hit with regulations that don't say control your sediment, control your bacteria. They're going to say control your impervious cover. And it is very scale dependent. This is a watershed-wide thing, so most of the other speakers will tell you to focus on impervious cover at the site level is totally the wrong way to go about it. So we look at our 19% slice, and if we look at change, this is a pretty basic graph as you can get. The big box is geographically correct. If you smushed all those red pixels into one big box, that's how much development we have in Connecticut in 1985, and we added the little box, about 145 square miles in the period between 85 to 2006. But if we chunk this up in terms of towns again, because we always do this with our clear data, so now you're looking at percent developed land by town. And the warmer colors denote higher percentage of developed land or impervious cover as you zoom around the state. And you kind of see here the idea of the I-95 to I-91 traditional highway corridors. And if we segue over to 2006, that happened a little faster than I planned, but let's do it one more time. And you can see a general, or I can pick out a general kind of reddening of those same two quarters. And if you look at the land cover, you're thinking, well, that's not too bad. You know, we seem to be developing percentage-wise in those same two quarters. But that's not really what's happening. What we're seeing here is the legacy of 200 or 300 years of growth in those areas. So the percentages are still very high in those areas. But let's look at this graph. This is, sometimes all the maps and graphs get confusing, but this is change. So these are added acres in this time, not percentage, but I'm looking at sheer acres of added development during that 21-year period. Now, so there's a little bias here towards the large towns when we look at overall acres instead of percentage. But what this shows us, we call this the hotspot map, although it's not colored very well. And what this shows us is those darker colors have had more added development, and many of them are not in that central corridor and all the traditionally developed areas. In fact, we've got a couple of very recognizable hotspots. We've got this area of the country, which some people would call the casino effect. We've got this area on the lower left, which, I don't know, I can't believe I have to commute to New York City all the way from this second-tier suburb effect. And then the north of Hartford, you know, commuting all ways to Boston, Springfield, Hartford, and you name it, with a lot of growth in that area. We pick everything apart in the website at the town level as well. This is a little map of New London. You can go through and get maps and change maps. I just wanted to show you one example, just to show you. This is Manchester, which experienced the greatest increase in acreage of development during our study period. So again, you're looking at red is developed, yellow lawns, etc. It's 85. And that's 2006. So if we back up again and you direct your attention to the upper border of Manchester there, with whatever the town is to the north of Manchester, and all those brown agricultural fields in the other town, if you focus on that line, you'll see a tremendous amount of infill of large monolithic development, which we can't say for certain with land cover is large commercial industrial development, but we actually know it is, and from the shape and also from the fact that we know that it's Buckland Hills Mall and Evergreen Walk and all those types of things. But you can't keep toggling back and forth, so we provide change maps and change data. This map shows change. Every single colored pixel in this map is new development in that period, and the color scheme, the legend, depends on when it occurred during our 5 iteration points of our study. So you can see some phasing of the different new development. But something we added in our recent update of the study, this is the exact same map in terms of the exact same pixels are colored, all the new development, but the color scheme denotes from which land cover that development was carved. So we did this in order to inform debates about loss of farmland versus loss of forest, etc. So the development colored green came from forest. The development that came from agricultural lands is brown. So as we look at that change map of Manchester, I just wanted to mention, now this is the town with the greatest percent increase in development in, I think it's Oxford, Connecticut, and you can see that pretty well. You can see the patterns of development are quite different. As I said, it's kind of monolithic commercial development in Manchester, and all those pretty little squiggles in Oxford, which, again, we can't say with land cover, but we can pretty much infer that they are residential subdivisions. Your eye, again, can pick this pattern out, and we would say there's a lot more sprawl pattern going on in one than the other. We have not yet quantified this at CLEAR, but we do have a model. We have a grant proposal in to run the model on our data so that we would actually be able to quantify this and be able to say, well, the town on the right, the new development was 3% infill and 45% outlying and 6% perforated way out in the hinterlands. And so quantify it along a scale that would relate very closely to the density concerns that smart growth advocates have around the country. And we're really excited. We hope we get that grant. So let's look at the next one, which is the most common. 59% is by far the most common land cover in Connecticut. New England, by the way, was the only region in the country maybe 20 years ago that was gaining forest cover. And that's because of the conversion of our agricultural lands, which it could be a good or bad thing, depending on your viewpoint. But now that's reversed, and we're seeing, of course, we're not seeing an increase in forest cover, we're seeing a decline, which I think I'll show you. There's a million values to forested land, and we don't have time to get into them here, nor am I a forester. But there's a lot of research to show that they're important to wildlife, water, a lot of the climate change concerns that we have in terms of carbon sequestration and temperature regulation and all sorts of other things. And the interesting thing is, for such an important land use, it's very much treated in local land use plans for the most part as nothing. It's not improved, it's excess, it's waste, it's not anything. It's a nothing between the something. That's a quote from one of my colleagues. And so one of the things we like to do talking to towns is to see if they can more proactively address the forested component of their landscape. Well, this literature is not nearly as robust as the impervious cover, but there are a number of studies out there that relate the total amount of forest cover in a watershed to the health of the stream or the receiving water. And this is our sub-regional watersheds. There's 300 and some odd in Connecticut. Darker the green, the more forest is in that watershed, and the darkest green color is 65% and above, which is what the literature pretty much says is indicative of healthy water quality. And you can see that we have a decent amount of those dark watersheds left in the state. I don't know what this is supposed to mean, so we'll just, yes, sorry. So here's our forest cover. Sometimes, I don't know. Now I've just grayed out everything but the forest, so you can see our forest cover in 2006. It looks like a pretty green map. You step away and you go, it's pretty green. But we look, again, at this is the same type of change map in total acres of where we're losing forest land, and you pretty much see that same pattern that we saw of increase in development of the different nodes, the southeast node, the north of Hartford node, and the second tier Fairfield County node of where we're losing forest. But that's forest quantity. And remember, we're talking about land cover, which is really urban forest canopy counts to us as trees, if there are enough trees for us to be able to sense it with the sensors. So what we're really talking about forest cover is forest quantity, but what do we know about forest quality? Well, I personally know nothing about it, but we can tell something about the change or the nature of it. This is the result of a forest fragmentation model, which is very similar to the one we want to run on the urban land. It basically takes every single pixel, billions of them in our data layer, and relates what's on that pixel to what's surrounding it. And what we're looking at here, the dark green areas, are what we define with our parameters based on some research as core forest. So if we back up again and look at the change, that's a much different picture than looking at just the forest cover. So our model, not to belabor the point, but to just relieve, one slide relief from all these darn maps. Core forest is self-explanatory, forest surrounded by forest. Perforated would be if you punch a low-density residential, we can't even see the driveway of that house, it's right in the middle of the forest. Edge is an important ecological concept, and here we're talking about a physical concept of forest next to non-forest in a long linear way. And finally, patch forest, which is really urban tree canopy, so trees surrounded by the predominant land cover of development. This is what our maps look like close up, and again, we provide them at the watershed and the town level on our websites. We use 300 feet as our guiding principle in our analysis, mostly based on work done here in the Northeast by Tim Forsman up in Harvard about let me see, how do I say this? The depth into natural land, I can't say this. The range, the impact of roads and how deep the impact of roads particularly goes into a forested landscape. How about that? So if we look at our forest fragmentation categories in our latest data, we see that less than half of our forest cover is core forest and a great portion of it is edge. And if we look at this, trends over time, we just see a fairly steep decline in the green line of core forest, and all the other three of the degraded forest types, if you call them that, are all slowly increasing. And if we say, well, where did the core forest go? Where did that lost forest go in that 21 years? 19% of it went directly to being a house or a subdivision or a parking lot, but most of it went to turning into the perforated, the low density, and edge, which would be slightly higher density development. And so what we do see, though, is that the other categories are staying fairly fairly uniform, because we're breaking into smaller pieces and everything continues to break down. But the first one that we're breaking up, the core forest, is the one that's really suffering. I want to have kind of a subset of forest, or at least vegetation related, and talk very briefly about Streamside, riparian corridors. These areas provide a whole host of benefits as well, and particularly for those of us in the water world in terms of stabilizing waterways and processing pollutants. And again, there is literature, but not very much at this point, that tells us that vegetated buffer strips or vegetated riparian corridors can do somewhat to ameliorate the impacts of development on waterways. So we just completed a statewide riparian corridor study to just look at it closer up. So it's just our same old land cover, but we just took a line and drew it around all the waterways and wetlands, associated wetlands. So that's what it looks like, and then we did our typical change map, and again, so it was just a subset of our Changing Landscape project, but along these critical areas. If we look at where we're losing the most riparian corridor, these are the same sub-regional watersheds, and now the darker colors, the warmer colors, reflect more loss, but they reflect loss not overall wide in the watershed, but just along our 300-foot riparian corridor. So you can see some of the same hot spots, and definitely this area of the world again. And we actually have a colleague, Juliana Barrett, who's used this to begin to talk to communities in the Niantic River watershed, which is very close to here, about strategies to protect and restore riparian corridors. I probably try to go through too much, but if you look at this table, and we're moving now away from the stream, from the 100-foot zone to the 300-foot zone to our statewide or the town-wide data, you can see that there's less development right along the stream than there is a little bit farther away and then farther away yet. And also if you look in the right-hand column, you see that the change, the added development, is a little bit less in the 100-foot zone. We added a little more in 300-foot in terms of percent, so relative change, and the state average is 3%. We really want to tease out what's going on here, and we have not done so yet. If you look at this, you'd say, well, part of it is just simple geomorphology. It's rocky and wet next to the streams, and we're going to have less development there, and I think that's true. There may be some influence of our Connecticut State Inland Wetlands and Watershed regulations, which allows towns to set a buffer area, an upland review area, and be able to pass judgment to some extent on development in those areas. But we also know that it has to do with overall development pressure. This is a little graph which I took out of the major presentation last night. It takes too long to explain. But what you can look at is a regression analysis, and that shows a very tight correlation between the loss of vegetation in the riparian zones, the blue being 300, the red being 100, and the overall towns. So what we're seeing is loss in the riparian areas being in lockstep with the overall loss in the town. So that says to me that maybe those regulations aren't working all that well, and that overall development pressure is the predominant influence. I only have 2 or 3 slides on turf because we have not had any subsidiary studies on our turf component. Note though that at 8%, it's actually more than our agricultural fields at this point in 2006. This is a national slide. This is not clear research. This is from the Center for Watershed Protection, except for I added and in Connecticut. Turf is the fastest growing land cover in most urbanizing watersheds according to CWP, and according to our data, that's true as well. It's by a little bit, it's the fastest growing land cover category that we have. The other bullets are messed up because of the font effect, but basically to say these areas are not as benign as we tend to think of them. First of all, they're not that pervious. They know a lot of water runs off, and you have your kids and your dogs and animals sitting on your lawn for 20 years, or at UConn you have thousands of students tramping around the green areas. That's more like a green green cement than it is a vegetated surface. And then they have a lot of pollutants in them. And about 3/4 of our turf areas, and this again is national data, not ours, is related to residential lawns, which is no surprise to any of us. Lastly, we look at our agricultural fields. These little smatterings are our left agricultural fields, and again, this is land cover, so we're looking at what has a signal that looks like an agricultural field. We're not talking about agricultural areas like in some other studies, which means any land that's owned by a farmer, because that land, of course, can have development on it, it can have forest on it, etc. And that's our little box chart. So the big square is what we had in 1985, and the little square with the lines is what we nipped out of it by 2006. This is the same area change, and you can see a little bit different, but you can see mainly your eye is drawn to the loss of agricultural field acreage in that north of Hartford, Springfield, Hartford corridor area. We did a very simple study conceptually, but not so simple in terms of crunching the numbers. This is not our land cover data. This is soils data from the USDA that shows agricultural soils of prime and important to agriculture. And what we did is we just laid our land cover on top of it, cookie cuttered it, and looked at the land cover over and land cover change over those areas. And what we came up with is this graph. So on the left, you're seeing our statewide land cover breakdown in 2006, which is the same pie chart you've been hoping that you're not going to see again during the course of this presentation. On the right is the land cover over our prime and important agricultural soils. Now, three things about this. One is that there's more agricultural fields on the ag soils, which is a heartening thing, and that it's still not a whole lot. The second is that you can see that there's slightly more development and much more turf over agricultural soils. And that makes sense when you think about it, because the characteristics that make a good agricultural area, flat and well-drained soils, are also very good for development, very easy for development, and typically have no trees on them, so they build these kind of starter castles and other things that you've seen pictures of, and there's a high turf component in that type of development. And last, on agricultural fields, I'd say that even though forest cover is less than it is statewide over ag soils, it's still the largest component of the ag soil areas, and that brings into mind questions of sustainability and possibly banking some of these areas. No, it's not farmland protection, because that focuses on existing farms. We're talking about maybe protecting areas that could be existing farms in the future. Lastly, and my colleague Norm Garrick's going to be talking about transportation, something I would know nothing about. But here we are back at our ag fields, and I'll just point out to you that there's a high-speed rail application, which is a very smart growth oriented. We're a little bit involved in this project. We're going to do some affordable housing education. But you can see, that didn't work. All right, well, anyway, you can see that at that upper Connecticut River Valley, which is incredibly rich farmland, is also where we're concentrating our transportation-oriented development. And so we really have to be mindful of all the smart growth principles to protect. So let me just pick out a couple of facts, and you don't have to look at any more maps, really. We've added, if you look at the urban footprint of the two big winners on the left there, three big winners, we've added about 240 square miles, and we've lost a concomitant amount of forest and farmland in this 21-year period. That's about 4.8% of the state. That's either not too much or a huge amount, depending on who you talk to. I would point out, though, that 21 years is not a long time period in the history of Connecticut. In terms of development, we know that it's mostly impervious cover that has the impact on streams. We have quantified how much it cleared, but we have not yet quantified the form of the development, and we really wish to do that. And the big thing there, again, is the hotspots of new development are not along our traditional transportation corridors, but out in the hinterlands, so far from smart growth. Forest is our biggest land cover. At the sub-regional level, many of our watersheds are still in pretty good shape if you believe the literature, but a lot of our forest resource is fragmented, and it takes a lot of people like Robert Askins at Conn College and other biology and ecological experts to take our data and maybe do some further research to tell us just what that means. Riparian areas, we don't really know what's going on. We know that they're losing vegetation at a slower rate than the state as a whole, and we know it's very, very much tied to what's going on in their town, but we don't know how much local geomorphology or the Connecticut regulations have to do with what's going on there yet. And turf is our fastest growing, and it's as I said, far from benign land cover. And finally, ag fields. Ag fields are now less than what we've got in turf and grass. We have a higher rate of development over those ag fields. Forest is the largest component, so we still have a possibility of banking some of them. And we're going to have this opportunity test tube in the upper Connecticut River Valley to test how we can preserve ag fields and do smart growth at the same time. So I will conclude with the same picture. Because I spoke all about research, I talked very fast, I showed you a lot of maps, but in the end, the real picture is here. It's 9:45 on Wednesday night. These people have just heard 3 hours of public hearing testimony. Now they've chucked the public out. They're making some decisions. And these little case-by-case decisions are adding up to creating the landscape and the landscape change that I've just been showing you. And we do have a number of educational programs that work with these people to try to help them do a better job. So with that, I ran over by 3.5 minutes. I'm very sorry, my moderator. And spring is coming. I thought you'd appreciate a little green at this stage. So thank you very much.